Hello everyone, we'll be covering problem number 2 in last year's 2024 free response problems. This is a combination of kinetics, thermochemistry, and buffer solutions. We'll be working with maleic acid, a dicarboxylic acid, and generation of a gas. And it will be first asking us about the kinetics, how fast, for the heterogeneous reaction, how fast the reaction will go in a chunk or in grinded by smaller particles, and it will be developing into the concept of entropy and Gibbs free energy. Finally, it is looking at the actions of the deprotonation of this dicarboxylic acid and look at its Ka1, Ka2 value and focusing on Ka2, asking us to think about a buffer solution. Okay, so let's get started. The reaction is a maleic acid. So this one is maleic acid. When you look at the Lewis structure, this is a dicarboxylic acid. Let me draw the structure. The bond line formula is showing that it is a dicarboxylic acid. So we have C, carboxylic acid here, again, carboxylic acid here. Okay, this is dicarboxylic acid. And sodium bicarbonate is represented. This is, we are using this one as a weak base. And when a carboxylic acid and bicarbonate solution is mixed, it will be forming carbonic acid H2CO3. And because this one is 2 equivalents of bicarbonate, it will be forming 2 moles of carbonic acid, but it is unstable. It will be quickly decomposing into 2 moles of carbon dioxide. Here I need to write 2 and water, 2 moles of water. That's we see, and sodium malate is the salt. Okay, equal masses of this maleic acid chunk, and chunk is an important word here, chunk, and sodium bicarbonate chunk are mixed with enough amount of water at 20 degrees C. As a result, it was observed the reaction generates 0.0114 moles of carbon dioxide gas. Calculate the number of grams of CO2 produced. So this one is a very simple question. It is asking us about, do you know how to calculate the molar mass of CO2, this compound, molecular compound, and in combination with mole, convert mole into a molar mass. So carbon, when you go to the periodic table, we see it has 6 protons and 12.01 AMU of mass. Oxygen is 8 protons, it has 16.00 AMU. So then CO2 has 1 carbon, so 12.01 plus 2 of oxygen, 16.00. When you add up, it is 44.01 AMU, which is grams per mole. So when you have 1 mole of carbon dioxide gas, the mass would be 44.01 grams. This is a ratio. The ratio, always keep in mind using it as a conversion factor. So let's get started from the given amount, which is 0.0114 moles of carbon dioxide gas, and let's multiply by a conversion factor. Mole is given, so then mole of carbon dioxide gas must be written at the denominator and grams of carbon dioxide at the numerator. And from this molar mass, we know that 1 mole has mass of 44.01 grams. Then mole cancels out. We are left with the grams. So this is grams of CO2, and we are given 3 suffix right there. 3 suffix. So let's represent the answer with 3 suffix, which is 0.502 grams of carbon dioxide gas. Why we do this? Why do we need this type of conversion? Because we cannot measure moles directly in the lab. What we can measure is either mass by using the balance or the volume by using a graduate cylinder or other or pressure, something we can measure directly. That's why we need to do practice conversion between mass and mole number. Second problem now is this one is gas generation reaction, 2 moles. Here let me correct it, 2 moles of CO2, and CO2 gas produced at 20 degrees C was collected, found to have a pressure of 1.25 atm. So this one is a collected in a container, and when you stick in a pressure gauge into that container, we found that it has a pressure of 1.25 atm. And then temperature, we are using thermometer to measure the temperature, 20 degrees C. We already know the mole number is 0.0114 moles. So then, in this case, we need to use ideal gas law, PV equals nRT. Here, P is given as 1.25 atm. Remember, pressure must be atm unit in order to use this ideal gas law with the gas constant R value of 0.08206 liter atm per mole K. Pressure must be in atm unit. Volumes is unknown, and N is 0.0114 mole of carbon dioxide gas, and T is 20 degrees C. And then we need to add 273 or 273.15 to convert it to temperature. Remember, the temperature must be a Kelvin unit. For any gas equation, we need to use Kelvin unit, so it is 293.15 Kelvin. The sigfig is up to the first sigfig. Alright, so based upon this one, let's find out the amount of volume. So PV equals nRT, let's divide both ends by P, then P cancels out. V is equal to nRT over P. We are ready. The unit of P pressure is atm. Yes. The amount of mole number is mole. Good. Temperature in Kelvin unit. Check. We check everything. Now we are ready to plug in. V is equal to 0.0114 mole times 0.08206 liter atm per mole K. Then everything will cancel out, times 293.15 Kelvin divided by the pressure, 1.25 atm. Because we use a proper unit, everything will cancel out, mole divided by mole, Kelvin divided by Kelvin, atm divided by atm. We are left with the liters right there. The unit will be liters. And then calculate the value with 3 sigfigs, which is 0.219 liters. Okay, the volume of the container would be 0.219 liters. So problem A is relatively simple, asking us converting the mole number into mass, and then using the ideal gas law, because this is gas evolution reaction, using the ideal gas law to find the volume of the container. The ideal gas law is often used to calculate the volume or the mole number. And previously, the previous question, AP free response problem, is asking us to find out mole number. In this problem, is asking us to find the volume. And B, second experiment, the same condition, but the chunk was grinded before combining with enough water. What happens to the surface area of the reactants? Definitely when it grinded, surface area is increasing. And then this is heterogeneous reaction. First, we need to dissolve this one into the solution, and surface area is really proportional to the reaction rate. The rate determined step for the overall reaction is the dissolving of the solids. Would the time for dissolving the solids be longer than, shorter than, or the same? Must be shorter, because it has more surface area, then it is more exposed to the water molecules. Water molecules will come and then So more water molecules will have access to the surface area, so then the dissolving will be occurring faster. And next problem is, now when the reaction is complete, will the volume of CO2 gas at the end of the second experiment will be greater than, less than, or equal to the first volume? It will be equal. Okay, so then kinetics. Kinetics is affected by the surface area. Kinetics is a function of the surface area for this heterogeneous reaction. But the thermodynamics is not affected. The spontaneity of this chemical reaction is not affected. So then when the reaction is going to complete, the amount of the, it takes longer for the first reaction, definitely, but at the end of the chemical reaction, the amount of carbon dioxide gas will be the same. Now, in a set, trials 3 and 4, and when they increase the mass of, the amount of those maleic acid is kept the same, but when we make more of sodium bicarbonate solution, then the moles of carbon dioxide produced also increased. Then it's asking, based upon data, identify the limiting reactant in trial 3. Okay, so let's analyze the reaction data. And then first, let's get started from the definition of a limiting reactant. Limiting reactant is reactant that runs out first. In a chemical reaction, when the reaction proceeds, runs out first, and it determines the theoretical yield. So determines yield. Theoretical yield, that's limiting reactant. Now let's look at, so here the mass of maleic acid 3 and 4 is same, but mass of sodium bicarbonate is increased by 0.348 times. And then look at the moles of CO2. This is again increased by 1.348 when you get the ratio. So then when the mass of sodium bicarbonate is now increased 1.3 times, then moles of CO2 is also proportionally increasing. It shows that the NaHCO3, this is limiting reactant. This is determining the amount of the product. So if more amount of limiting reactant would be added, yield will be increasing proportionally, and this data exactly matches with this definition and property of a limiting reactant. Next problem is a thermochemistry problem. This is reaction entropy is positive, using particle reasoning, level reasoning, explaining why the entropy increases as the reaction progresses. Here, the reactants, we have 1 mole of maleic acid and 2 moles of sodium bicarbonate, they are combining. So then 1 mole plus 2 mole, 3 moles. 3 moles of reactants are used and consumed. As a result, how many moles of products are generated? 2 moles of carbon dioxide, 2 moles of water, and 1 mole of sodium oxalate was generated. So 5 moles of products produced. So then in net number of moles is 5 minus 3, 2 moles. 2 moles of compounds are generated, are released or generated, increased as a result of this chemical reaction. So it has more degree of freedom, more higher degree of freedom is increasing. That's the definition of entropy. So then that's why entropy, reaction entropy is positive. Now let's move up to the next problem. The student claims that the reaction is thermodynamically favorable at all temperatures, And because delta S is positive and the reaction is endothermic. Do you agree or not? Okay. Thermodynamically favorable, this one meaning Gibbs free energy. So Gibbs free energy is negative. Remember, thermodynamically favorable meaning delta S of the universe is positive, and when it translates into focusing into the chemical reaction, our system, then we can tell delta G is negative. So then delta G is composed of delta H minus T delta S. And remember delta H and delta S, they are relatively constant. They are changing a little bit, but relatively constant. So we can treat them as constant for our estimation, okay? And what is changing is only temperature. Temperature is variable, okay? So we can draw the graph of delta G versus temperature. So let's draw a graph, okay? As temperature increasing, let's write Kelvin unit temperature and delta G as a function on the y-axis. And the criteria for spontaneity is 0. When the delta G is less than 0, it is spontaneous. When the delta G is positive, the reaction or chemical change is non-spontaneous. Here we know delta H. Delta H is endothermic. Endothermic meaning positive. The reaction is endothermic. The enthalpy level of the product is higher than enthalpy level of the reactants. And delta S is positive also. Here, let me write delta G as a function of temperature. Delta H, so this one is y-intercept. And plus negative delta S minus T delta S, let me write it, rearrange it, negative delta S times T. So this is slope, negative delta S slope. Because delta S is positive, negative delta S is negative. Okay, so then I can draw a graph generally like this way. So the y-intercept is delta H. This is positive. The slope is negative delta S, negative. Okay. And that is the line. The line of this delta G is a linear line with respect to temperature. At a certain temperature, it is intersecting with the 0 line. Let me call this one T sub C, a critical temperature. And above the critical temperature, the value of delta G is all positive. Here in this region, the reaction becomes non-spontaneous because it is positive. Because delta G is positive. And above the critical temperature, it becomes now negative and it becomes spontaneous. Delta G is now becoming negative. So then I do not agree with this claim. The reaction is not favorable at all times. At high temperature, when the temperature is higher than the critical temperature T sub C, then the reaction is spontaneous. But when the temperature is low, specifically lower than the critical temperature, delta G is positive and the reaction is non-spontaneous. Now let's move up to the concept of buffer. Problem is now combining this dicarboxylic acid with the acid-base chemistry. So this one has 2 carboxylic acid. Let me draw the reaction again, structure again, 1, 2, 3, 4. So it is carboxylic acid right there. So this is acidic proton. So it will be protonated. Again, 2. I have 2 carboxylic acid. It can be protonated in sequence. So when the first term then is protonated, the Ka1 value is now 10 to the negative 2. Let's look at the order. When the remaining hydrogen is protonated again, Ka2 value is now 10 to the negative 7. And this is always a situation. When multiple of them, multiple protons can be protonated, always Ka1 is much bigger than Ka2. And again, if we have a third proton that can be protonated, that is again much Ka2 is bigger than Ka3. Remember those relative properties. 10 to negative 2, 10 to negative 7, it is 5 order difference. Very large difference between these two values. Okay, calculate the pKa2 value for this hydrogen malate ion. Okay, and look at the definition of pKa value. It is negative log. Anything that p function definition negative log of Ka2, and simply plug in those value into Ka2. So it is negative log of 8.5 times 10 to the negative 7, and write this one with 2 decimal places. So then the value is 6.07. Okay, why this pKa2 value? The problem, the author of this free response question is asking us because of G of a pH. We want to prepare pH value of 7.0 solution, and the second one is now proper to prepare this solution. I'll be explaining in the next problem. Now a buffer solution with a pH of 7.00 is prepared with this hydrogen malate ion and malate ion, those acid and base, both of them preparing this one. Calculate the ratio of the malate ion over this hydrogen malate ion concentration. Okay. Remember that first the ratio of conjugate base and a monoprotic acid must be in between 1 and 10. This is a buffer range. Okay, this is very important property. In order for a buffer system is functioning properly, the ratio of, buffer has weak acid and its conjugate base, both of them in comparable amount. How much is comparable? 10 times. The ratio of a concentration must be within 10 times range. It means when you plug in this one into the buffer equation, pH can be determined from pKa value of the acid and the ratio between the conjugate base concentration and acid concentration. When you use this equation, combining them together, we come to the conclusion that because pKa is a constant, pK value is not changing as long as the temperature is given same. So pH of the solution of a desired buffer must be within pKa value +1, pKa value -1 in this range. Okay, what about our pH? Desired pH is 7.00. Our pK value is 6.07. We just found out. So the difference is now 0.93. So it is within 1. Okay, the difference, let me absolute value, take the absolute value. The value must be within 1 range. And this is close to 1. This is a little bit unstable. When the value is close to 0, then the buffering system is very stable. This is slightly unstable, but still doable. The buffering system is working. And let's calculate the ratio to give this ratio. And then let's write the equation. So pH is equal to pKa. Let me erase it, this one. Okay, pKa plus log of the conjugate base, which is malate ion, C2O42 negative, and here the acid is hydrogen malate. Okay, let's write it like this way, and let's rearrange it. So let's subtract the pKa from both end sides, pKa. Then it cancels out. log of C2O4 2 negative over hydrogen malate, the ratio is pH minus pKa. I just calculate right there, pH minus pKa, which is 0.93. Now let's take anti-log on both end sides. Anti-log on both end sides. Then C2O4, 2 negative over hydrogen malate ion concentration will be base 10. The log, we are using common log base is 10, 10 to the 0.93 power, which is 8.5 times. So this is our final answer. Okay. So this one is very important property. Buffer is very important in biochemistry. When we apply our concept chemistry to understand in the property of life, something like medical field or biochemistry, microbiology, biology, we need to make a buffered solution. The first step, understand the system is making very clean system with the same pH, with the same salt concentration. We are studying this one in this clean buffer system first, and then we want to apply the same concept into a serum and then whole blood in this order. That's the order. So we need to understand the property of buffer very well. And the first thing is, in order to make the buffer system functioning properly, the ratio of conjugate base and its monoprotic acid, the concentration ratio must be within 10. And here, and then we were able to use this Henderson-Hasselbalch equation to calculate the ratio quantitatively. Okay, then I will see you in next video. Thank you.